It won't grant permission to allocate the resources to the process. We cannot have the mutual exclusion property as the only one property to avoid the deadlock prevention. The challenge here is to save the state of this execution, that is process P1. We have used deadlock prevention and deadlock avoidance. How deadlocks are detected? Hello and warm welcome to one and all. It is Dr. Ravikumar YB, Department of Computer Science, Vidhyaashram, MYSURU, First Grade College, the Temple of Excellence. In today's class, we shall see about the deadlock prevention. What is the meaning of deadlock? As I have already discussed with you all in the previous sessions, that the deadlock can occur only when there is a cyclic graph. That means when one of the resource is going to be assigned to one of the process and the same resource is required for another process, that becomes a deadlock situation. Because suppose if there are two processes, that is process P1 and process P2, where process P1 has already held one of the resource and process P2 is waiting for the resource which is held by process P1, and the vice versa of it, that leads to the deadlock situation, that is a cyclic graph. In order to avoid and prevent such type of deadlocks, we will have certain mechanisms. Let me explain about those mechanisms in today's session. The deadlock prevention can be done by following these four different conditions. The first one is mutual exclusion. Second one is hold and wait. Third condition is no preemption. And fourth condition is circular wait. Let me explain each of these conditions one by one. The first one is mutual exclusion. What is the meaning of mutual exclusion? As I have already discussed with you, that is mutually exclusive property means what? Suppose if there are two processes, mutual exclusive, that means only one of them is permitted to access the resource. That is the meaning of it. Not always possible to prevent deadlock by preventing mutual exclusion. That means making all resources shareable, as certain resources cannot be shared safely. That means certain resources cannot be shared safely, so we cannot have the mutual exclusion property as the only one property to avoid the deadlock prevention. There are many other conditions like hold and wait, no preemption, and circular wait. Let me see to the details of the hold and wait as well. What is the meaning of hold and wait? We have two approaches here, but both of them have their disadvantages. That is, the resource can get all the required resources. That means a process can get all the required resources before it starts execution. That means whatever the resources required for a process can be assigned to it before the actual execution begins. This will avoid the deadlock, but will result in a reduced throughputs. The total number of time, that is the total time taken by the number of processes, is called as a throughput. That affects the throughput of that program execution by the process. If that is the case, the throughputs as resources are held by processes even when they are not needed. That means when process P1 is there, P1 has held R1 and R2, but P2 is another process require R2, R3 and R2, but in this case R1 and R2 is held by process P1, but R2 is not at all required for it. However, the process P1 is assigned with resource R2. In this situation, the same R2 resource is required for P2, that leads to the reduced throughput. That means it has to wait until the process P1 executes the complete program. That is the meaning of hold and wait. It has to wait until it is going to release the resource R2, which is held by the process P1. So hold and wait can be one of the conditions to prevent the deadlocks. They could have been used by other processes during this time. That means at the same time, if the resource is released, this would have been used by process P2. Thus, we are going to prevent this deadlocks. The second approach is to request for a resource only when it is not holding any other resource. That means it requests for a resource only when the resource is not held by another process. Otherwise, it has to wait. That is the meaning of the second approach. That means the starvation is going to be prevented with the help of not requesting the resource which is held by the other process. Suppose if there is any resource which is not at all held by any other process, then we can allow the process to request for that resource. That is the second approach of hold and wait. Moving on to the no preemption, first let me tell you what is the meaning of preemption. Suppose when the process is executing a program, if any higher priority process comes into the picture for the execution, then it has to preempt or switch over from the current process to the next process which has come with priority. That is called as a preemption. No preemption means there is no possibility of switching over from one to the other process. That is the meaning of no preemption. If that is the case, we will see two approaches here. That means if a process requests for a resource which is held by another waiting resource, then the resource may be preempted from the other waiting resource. That means when a process requests for a resource which is held by another process, then the resource may be preempted from the other waiting resource. That means the other waiting resource is preempted. That means given permission to the process to use it. That is the meaning of preemption. No preemption means it is not permitted to use the resource which is held by another process. That is the third property. In the second approach of this no preemption, process request for a resource which is not readily available or all other resources that it holds are preempted. Please read this, preempted. That means once it is released, we may allow the process to make use of those resources which is preempted by other processes. That is the meaning of this second approach with respect to the no preemption. Then the challenge here is that the resources can be preempted only if we can save the current state can be saved and processes could be restarted from the same state. That means the challenge here is when the resource is allocated to certain process, that is R1, R2 is allocated to process P1. If process P2 requests for the resource R2, then process P2, the challenge here is to save the state of this execution, that is process P1. State of this process, current state of execution must be saved in which data structure? Process control block. Then it can resume the operation of process P1, that is the use of resource R1 and R2 with process P1 from the state where it was left. That is the meaning of this. That is the challenge here. That is giving permission to the process to use the resources and then resuming the operation from where it was stopped. That is the challenging condition with no preemption. If that is the case, we have the fourth condition, that is circular wait. We have to avoid the circular wait to break the cyclic graph. If that is the case, to avoid circular wait, resources may be ordered and we can ensure that each process can request resources only in the increasing order of these numbers. What is the meaning of this? Circular wait. 0, 1, 2, 3, 4, 5, 0. Process P0 is waiting for this resource. Process P1, P2, P3, P4, P5. So we have all these resources here. The resources may be ordered and we can ensure that each process can request resources only in the increasing order of these numbers. That means process P1 is there. Resource R0 is here. R1, R2, R3, R4, R5. So we have these resources which are ordered in the increasing order, that is R0, R1, R2, R3, R4, R5. So whenever process P0 wants, we can assign resource R0 to P1, R1 to P1, R2 to P2, R3 to P3, R4 to P4, R5 to P5. So on like this. So that gives a condition of circular wait. That means it avoids a circular wait. That is from process P5 to P0. Again, it comes back to it. So these resources are allocated to processes by avoiding the circular wait. That means what? That means we have a resource R1, R2, R3, R4, R5. We have these resources here. Then this resource R1 is assigned to one of the process, R2 is assigned to another process, R3, R4, R5. Then R1 is used once again. So with this, we are going to avoid the circular wait. That is, we can avoid the circular wait with these options. So we have these four conditions. The very first condition is mutual exclusion. Second one is no preemption. Third one is hold and wait. Fourth one is circular wait. These four conditions must be satisfied by the operating system to prevent a deadlock within a system. Then, which is the next one? Deadlock avoidance. How can we avoid the deadlock from the operating system? That means deadlocks can be avoided by making use of prior knowledge about the usage of resources by processes, including the resources available, resources allocated, future requests and future releases by processes. What is the meaning of this? Before starting the execution of a program, we will consider the requirement. That is, first the prior knowledge. What is the process and which process requires how many resources? That means the total number of resources required for process P1, total number of resources required for process P2, total number of resources required for process P3 are considered here at the prior knowledge. Once with this prior knowledge, we will start considering the resources that is required in future. Already how many number of processes and resources are allocated to process are considered. Then in future, how many resources are needed for these processes? All those things are calculated to avoid the deadlocks. If that is the case, Banker's algorithm is one of the important algorithm that checks whether the deadlock can be avoided with the operating systems. If that is the case, most deadlock algorithms need every process to tell in advance the maximum number of resources of each type that it may need. All these algorithms must inform to the operating system that these are the number of resources required for each process. The operating system may plan according to the requirement of this process and grant permission to use those resources by the process. So this operation and granting of permission must be done by the operating system. Based on all these information, we may decide if a process should wait for a resource or not, and thus avoid chances of circular wait. That is, this circular wait helps you to land up in deadlock. If we avoid the circular wait, that means a cyclic graph that leads to an regular system without any deadlocks. If a system is already in a safe state, we can try to stay away from the unsafe state and avoid deadlock. When shall we say that the system is in safe state? When the number of resources available is equal to or more than the number of process requests, then we say that the system is in safe state. Otherwise, it has to allocate the resources according to the requirements of a process in terms of schedule. That is the meaning of safe state and unsafe state. If that is the case, deadlocks cannot be avoided in an unsafe state. That means when the number of resources required for a process is less than the resources available, then we say that the system is in a unsafe state. To avoid all those things, we will consider these options. That is, a system can be considered to be in a safe state if it is not in the state of deadlock and can allocate resources up to the maximum available. That is the meaning of this. Then, a safe sequence of processes and allocation of resources ensures a safe state. We have a safe sequence. What is the meaning of safe sequence? After P1, which is the next process to be executed, which is the next process to be executed, which is the next process to be executed. All these sequence is written here to indicate that all of the resources available within a system are sufficiently used by the processes. That is called as the safe sequence. Then, deadlock avoidance algorithms try not to allocate resources to the process if it will make the system in an unsafe state. Whenever we grant resources to a particular process, and if there is a lack of resource to other process, that leads to an unsafe state of a system. So in order to avoid such thing, the deadlock avoidance algorithm also suffer from low resource utilization problem. That means if the resources are used less in number for a process, then again that leads to a problem. That means low resource utilization problem. It has to be used sufficiently, whether it may be a CPU or it may an IO device or maybe any other resources, memory resources or anything that has to be utilized efficiently to make the system efficient. Then, resource allocation graph generally used to avoid deadlocks. Why we require this graphical representation? To check whether there is any cycle of graph is available. If there is no cycle in the resource allocation graph, then there is no deadlocks. If there are cycles, there may be a deadlock. The same thing. If there is a cycle in graph, we say that there is a deadlock. If there is no cycle in graph, we say that there is no deadlock at all. If that is the case, if there is only one instance of every resource, then a cycle implies a deadlock. Vertices of the resource allocation graph are resources and processes. The resource allocation graph has edges, that means request edge and assignment edge. A request edge is indicated by this and an assignment edge is indicated by, we have two different types of edges. One is this type of edge and the other one is this type of edge. This is called as request edge and this is called as an assignment edge here because we have already assigned resource to the process, but in this case it has a request to be assigned to that process. That means process is requesting for a resource, but it has not yet been assigned to the process. That's why we represent it by dotted or dashed lines. An edge from process to resource is a request edge and an edge from resource to process is called as an allocation edge. A claim edge denotes that a request may be made in future is represented as a dashed line. Please see to it here. Whenever a process requests for a process, we say that process P1 is requesting for a resource R1. When there is a directed graph, that means directed edge from resource R1 to P1, we say that the resource is granted for use with process P1, so that this is called as an allocation edge. But there is also a chance of assigning resources to the process. That means a claim edge. A claim edge is indicated by dashed lines. That means process P1 is claiming for resource R2. That is the claiming edge. Based on claiming edge, we can see if there is a chance for a cycle and that grant requests if the system will again be in a safe state. That means whenever a process requests and claims for another resource of a process, and even then claiming of resource of a process, if there is no chance of unsafe state, then the system will grant access to process to access the resource, so that the system will remain in the safe state. If you consider this, the claim state, that means the claim edges below, these are called as a claim edge. Process P1 and P2 are claiming for resource R2, but resource R2 is assigned to process P1. P2 is also waiting for resource R1. So P2 is requesting for process R1 and claiming for resource R2 here, we have resource R1 already assigned to process P1. In addition to this resource R1, P1 also requires resource R2. That means R2 is allocated to P2, and if P1 requests for R2, there will be a deadlock. Because both of these processes are competing for the resource R2. That's why we have a deadlock there. If you look at this diagram, you will see that the resource R2 is assigned to P2, and further P2 is expecting the resource R1, which is held by process P1, but process P1 is waiting for claiming for this resource R2. So again, there is a chance of deadlock. That means the resource allocation graph is not much useful if there are multiple instances for a resource. In such case, we use Banker's algorithm. The Banker's algorithm are used in these situations. When there is a possibility of deadlock, we use the Banker's algorithm to check whether the assignment of resources to the process will leads to the system in a safe state itself or not. If it leads to a safe state, we will grant permission to the process to make use of the resources. Otherwise, we won't grant permission to make use of the resources by a process. In this algorithm, every process must tell upfront the maximum resource of each type it needs, subject to the maximum available instance of each type. That means, for example, resource R1. Resource R1 is having 2 instances or 3 instances of it. R2 is having 2 instances of it. Now, I have 3 instances of resource R1, 2 instances of resource R2. By granting the permission to these resources by the process P1 and P2, if there is any possibility of unsafe state. Suppose if it is safe state, we grant permission to use those resources for any of the process. But if it leads to an unsafe sequence, then it is not granted at all. And also one more thing. The maximum requirement of this process is calculated with reference to the maximum available resources with the system. Then, allocation of resources is made only if the allocation ensures a safe state, else the process needs to wait. The same thing as I told right now. That means the allocation is made only if the system leads to a safe sequence. Otherwise, it has to wait until the resources are released by other processes. The Banker's algorithm can be divided into 2 parts, that is safety algorithm, if the system is in a safe state or not. So the Banker's algorithm are divided into safety algorithm also. That means that derives the safe sequence of a system, whether by allocating resource to the process will remain the system in a safe state or not is checked and verified with respect to the safety algorithm. Then the resource request algorithm makes an assumption of allocation and see if the system will be in a safe state, if the new state is unsafe. We have 2 different types of that. One is safety algorithm. Second one is resource request algorithm. This checks whether the system is in a safe state or not by considering the safe sequence of a system. This resource request algorithm makes use of the request algorithm that makes an assumption of allocation and see if the system will remain in a safe state. If the new state is unsafe, then it will not grant the allocation of the resources. That means the resources are not allocated and the data structures are restored to their previous state. In this case, the process must wait for the resource. That means by allocating resource to the process, if it leads to any unsafe state in the next sequence, then it won't grant permission to allocate the resources to the process, so that the process must wait until the resources are granted for use with that particular process. That is the meaning of it. Deadlock detection. We have used deadlock prevention and deadlock avoidance. How deadlocks are detected? Using these resource types. If deadlock prevention and deadlock avoidance are not done properly, as deadlock may occur only if the things are left to do is to detect the recover from the deadlock. That means recovery of deadlock. How can we recover the system from deadlock? That means if all resource type has only single instance, that means one instance of R1, one instance of R2, one instance of R3, then it is very difficult. So then we can use the graph called wait for graph, which is a variant of resource allocation graph. The variant of resource allocation graph is wait for graph that helps you to identify how many resources are needed for which of the processes. Here, vertices represent the process and a directed edge from P1 to P2 indicates that process P1 is waiting for a resource of P2. That means if there is a node like this, we say that this is the process. Suppose if there is an edge from P1 to P2 or P4, we say that there is a request edge from process P1 to process P4. Like in the case of resource allocation graph, a cycle in a wait for graph indicate a deadlock. So the system can maintain the wait for a graph and check for the cycles periodically to detect any deadlocks. It periodically checks by assigning resources to the process if there is any chance of a cycle in a graph. If so, it avoids allocating those resources to the process so that the system remains in an uncyclic graph, uncyclic graphical format. So the wait for graph is not much useful if there are multiple instances of a resources, as a cycle may not imply a deadlock. That means if there are multiple instances of resources like P1, R1 has multiple instances, R2 has multiple instances, R3 has multiple instances, then there is no chance of having a deadlock, because when P1 requests for resource R1, one of the instance of R1 is given to it. When P2 requests for R1, another instance of R1 is given to it. So there is no chance of deadlock. But this chance of deadlock will occur only we have when the single instances of resources are available, that is R1, R2 and R3. Then there is a possibility of deadlock. In such case, we can use an algorithm similar to Banker's algorithm to detect deadlock. We can say that if further allocations can be made or not based on the current allocations. That means the current state of the system is considered for detecting whether the deadlock can occur or not. So if you look at this diagram, P1 is requesting for resource R1, but resource R1 is assigned to process P2. P2 is requesting for R2, but R2 is assigned to P1. So this leads to a cyclic graph. This cyclic graph leads to a deadlock situation. Once a deadlock is detected, you will have to break the deadlock. How can you break the deadlock? By assigning or releasing one of the resources. It can be done through different ways, including aborting one of the resource or more processes to break the circular wait condition, causing the deadlock and preempting resources from one or more processes which are deadlocked. That means what? That is releasing one of the resources or preempting the resources of the process to another process, so that the process will continue with the execution of the program. So with this, I'm concluding the session of deadlocks. Thank you very much. Thank you one and all.